Hello everyone, welcome to lecture number 6. So today we will continue solving few special types of ordinary differential equations. So in the last lecture we stopped right just before here. So we need to solve this equation y double prime minus ky is equal to 0. So as usual, let's assume that y is equal to e to the power lambda x as a general solution. So then the auxiliary equation obviously becomes lambda square is equal to k. So I am just solving it in shorter fashion. So lambda square is equal to k means lambda is equal to plus or minus root over of k, where k is a constant. So therefore the general solution becomes y of x is equal to c1 e to the power plus root over of kx plus c2 e to the power minus root over of kx. So the two roots of k, that is plus of root k and minus of root k, would appear at the exponential form like here. So this becomes the general solution, whereas obviously c1 and c2 becomes the constants of integration. So this is definitely one of the types. Now the most important thing is, what if k is equal to minus 1? So how do we solve that? So now let's quickly take a look at our second. So if we take k is equal to minus 1 in the previous example, so the previous differential equation becomes something like this: y double prime plus y is equal to 0. Now from that, by applying the same principle, we straight away get the auxiliary equation lambda squared is equal to minus 1. So that means if we are going to solve lambda, so lambda becomes plus or minus root over of minus 1. And we all know that this quantity is nothing but I, the imaginary quantity. So therefore, this becomes plus or minus I. Okay. So the general solution, of course, we can write y of x is equal to c1 e to the power plus ix plus c2 e to the power of minus ix. Okay. So obviously this is a complex number. Now the question is, can we write this expression in terms of something else? The reason I'm asking, because according to Euler's formula, e to the power of plus or minus I theta can be expressed as cos theta plus or minus I sine theta. Okay, so this complex equation can be transformed into some trigonometric expression. So therefore we need to replace e to the power ix and e to the power minus ix in terms of cosine and sine function. So let's do it here. So therefore we can now continue that yx is equal to this expression, and then we can replace e to the power ix in terms of Euler's expression. So c1 cos x plus I sin x plus c2 multiplied by cos x minus I sin x. Okay, now further we can break them from the bracket and we can segregate the real and imaginary parts. So like this, C1 cos x plus I C1 sin x plus C2 cos x minus I C2 sin x. Further, we can write it as, if we can take C1 plus C2 common, then we can write cos x. So this is our real part, plus we can write it like that, I, and then C1 minus C2 and sin x. So this is our imaginary part. So remember, these two are our constants now. So we can further replace as two new constant to simplify. So C3 cos x plus, we can write it I C4 sin x. Okay, so this is an alternate form of the general solution of the type that we are currently discussing. So this is one of the form, and we can write the alternate form. So alternate form was of course written on the top. So this is y of x. So the alternate form also y of x is equal to this one, c1 e to the power ix plus c2 e to the power minus ix. Okay, so this is the solution. So either of this, either this one or that one, is the solution of the particular ordinary linear and homogeneous differential equation that we are talking about. Now the question is, why particularly we solve this type to have this general solution? The answer is, in quantum mechanics, especially the wave equation, that means the vibration of one-dimensional string, we have to come across such type of equation. So let's also try out another example to see what is the implication of such general solution having a real and imaginary part. Okay, so just a little correction before we go forward, that C3 cos x plus I C4 sin x, this equation can also be written by taking the imaginary quantity within the constant itself. So the same equation can be written in a much simpler fashion, the C3 cos x plus C4 sin x, where C3 is the real constant and C4 contains the imaginary part. So therefore C4 becomes imaginary. So that was the whole thing we needed to understand all about. So now let's move on to our next special example of the type of the type of ordinary differential equation we just solved. The same thing now we are going to solve it. So now we come to a very special type of ordinary differential equation. So this is the type now you can recognize that we are talking about this one in this lecture. And this particular differential equation, I think you might have come across before, and if not, you will see that during this course, this equation would be a very important one and it would come back. So of course, if we can recognize this is in the form of y double prime ky is equal to 0. Okay, so this is our making the equation into a simpler form. So if that is the form, then obviously here what we can write, that omega square is actually our k. So if that is the case, so we can frame the auxiliary equation, and after framing the auxiliary equation in terms of lambda, we can solve that lambda is equal to minus omega square. Alright, so how we can further lambda square is equal to minus omega square. So now the thing is how we can solve lambda from this. So of course we can write minus omega square is equal to minus 1 multiplied by omega square. So of course then when we try to solve lambda, then it becomes root over of minus 1, so plus or minus root over minus 1 multiplied by omega, or simply this becomes plus or minus I omega. Alright, so if this is the lambda value, then obviously we can find the general solution. So remember, now the general solution is in the form of xt. So xt is equal to c1 e to the power plus I omega t plus c2 e to the power minus I omega t. Alright. So this is expressed in one form, and we are already familiar how we can express it in its alternative form. So, or we can write its alternative form as xt is equal to c3 cos omega t. Then you can tell me plus c4 sine omega t. So of course you can understand that these are the same one but in different form, and c3 is real part and c4 is your imaginary part. Means the constant contains the I. So you see how simply within 1 minute, using 2 or 3 steps, we can solve this differential equation easily. But remember, this is a general solution, and we still have to go further for a few steps because we still have to find a specific solution because some certain boundary conditions are given. So let's continue to solve it. So now we have to fit these boundary conditions into the general solution that we have just got to find the specific solution. Okay, so the condition says that at t is equal to 0, this general solution, the value becomes a. So let's try to solve it. Putting t is equal to 0 in this equation, we get x0 is equal to, putting t is equal to 0 makes this unity, so multiplied by c3 means c3, and this part becomes sine 0 is equal to 0. So it tells me that c3 is equal to a. So therefore we already solved the particular constant of integration c3 is equal to a. So now let's solve the second part by taking the second condition. So the second condition says that x prime 0, that means the first derivative of this equation at time t is equal to 0 becomes 0. So what's that first derivative? Of course, if we take the first derivative of this, so this becomes minus c3 omega sine omega t plus c4 omega cos omega t. All right. So whenever we now try to put t is equal to 0, so means here the sine omega t parts become 0. So this equals to 0 plus, and this part becomes unity. Okay. So what we get is the entire part. Just a minute. Yeah, so we get 0 plus c4 omega. So everything becomes is equal to 0. So this implies that definitely C4 must be 0, because already omega is given here and omega can be 0. So we now get the values of the two constants of integration, that is C3 is equal to A, and of course C4 is equal to 0. So if we take these two values of C3 and C4, then definitely we are able to write the entire specific solution. So the specific solution according to those boundary conditions becomes xt is equal to, so C3 becomes A cos omega t, and we have already found out that the value of C4 was 0. So xt is equal to A cos omega t. Now the question is, can you remember or can you recognize this kind of equation? Can you graphically represent it? So let's see how we can plot it. So before we go ahead drawing the graph plot, let's try to understand a few things. That here omega is actually angular velocity. So where omega is equal to 2 pi nu, where nu is the frequency. So how omega is defined like that? So 2 pi when expressed is in radian, it means a full circle. So omega means the number of times per second something completes a total cycle. Total cycle means a revolution containing the complete angle 2 pi. So frequency means number of times something fulfills a complete rotation, it becomes omega. That means number of complete revolutions per second. So therefore the same thing can also be written as A cos, instead of omega we can write 2 pi nu and then t. Alright. So now let's take a look at here that the values. So if when omega t is equal to 0, we can say xt is equal to 0. And when omega t is equal to pi by 2, then the value of, so sorry, here when omega t is equal to 0, the value of xt is equal to, this is 0, this is 0 means omega xt is equal to A, and when it is pi by 2, the value becomes 0, and when this is 3 pi by 2, the value becomes minus A, and so on. So therefore we will now try to draw the graph plot. So sorry, a little correction here. So there was a mistake. When omega t is equal to pi, this is minus A, and when omega t is equal to 3 pi by 2, this is 0. So we can now draw the graph plot like this. So this is the time axis t, and here we can have our xt. So at omega t is equal to 0 means here, that means when t is equal to 0, we have the amplitude A, and then the graph goes like that. So obviously, so this is xt is equal to 0 here, and this is pi by 2, and here and this is pi, and here this is 3 pi by 2, and so on. So once the graph comes back here, so it completes the full cycle. So this distance is actually 2 pi. Alright, so this is the graphical representation. So how does it look like? So I should better draw a graph like this. So it actually should look like this. So t versus x. So this is a cosine wave, or in other words, this is called a cosinusoidal wave. All right. So now we get the graphical plot of xt is equal to a cos omega t. And now we see that the solution graphically represents a cosinusoidal wave, so just like sine wave. So now also we see that this is a solution for a specific type of motion, and the motion is called simple harmonic oscillatory motion. In other words, a simple harmonic oscillator would give this the solution xt is equal to a cos omega t, the specific solution, and the corresponding graph plot is a cosinusoidal wave. So now you see that very casually we actually solve the differential equation representing simple harmonic oscillation. Okay, so now you see that this type of differential equation is really helpful and it has practical applications. So I guess discussion about the different types of ordinary differential equations and their solutions have been discussed well enough. So we stop it here, and in the next lecture we will actually start from the vibration of a one-dimensional string, that is a situation of a classical standing wave. So till then, see you in next lecture. Thank you.